So with vertical motion, the last scenario we have to look at is the free fall scenario. So we're going to go with the elevator. Now let's say you're in an elevator. Let's say somehow somebody cut the cables and the elevator is going to start falling. We're going to assume that friction is negligible, so the only force acting on you in this case is the force due to gravity. So your free body diagram is going to be really simple. So in free fall, that's all that's happening. You got that force of gravity trying to pull you back down to the ground. Let's look at this. Well, since the net force is down, we'll call the down direction positive. So all we can say is that the net force is equal to Fg. Or we know that Ma equals mg. Well, that's nice. We got Ma equals mg. The masses are going to take a hike. So what we get here is we get that the acceleration is equal to the acceleration due to gravity. And this is the definition of free fall. When something is free falling, its acceleration is going to be 9.81 meters per second squared. And in these questions, if you were doing the apparent weight questions, there is going to be no apparent weight in these questions because there's going to be no contact with a scale or any of that, because both objects, you and the scale, are going to be free falling. So in those cases, whenever we have free fall, apparent weight's going to be 0. Just to tie this up, this ties in nicely to the concept of weightlessness. So weightlessness is it's a specific phenomenon, and the only way to achieve this thing called true weightlessness, you'd have to be in very deep space, and even then, it's not really possible, because to have true weightlessness, you need the apparent weight to be 0. Okay, you can free fall, but the other thing you need is you need the acceleration due to gravity, or little g, to be 0. We haven't talked about it yet, but in the next unit, we're going to talk about Newton's law of universal gravitation, and we're also going to talk about gravitational field strength. You're going to find that achieving this condition, we can get this to be really small, but we can't get it to be exactly 0. So the whole idea of true weightlessness, it's more of a myth. Now, some of you may see people like, you may see Commander Hatfield, like his videos when he went up into space, or in this case here we have the late Dr. Stephen Hawking. You may see people kind of floating in space, or it looks like they're weightless. It's not quite simple. They are certainly experiencing forces. In these cases here, like for example with Dr. Hawking or anybody up in a space shuttle, if you see them kind of floating around, they are still experiencing forces due to gravity. In fact, they're always in free fall towards the Earth. But because they're also moving in circular motion, or they're moving in a tangential path, this gives the appearance that they're free falling. This gives the appearance they're floating in space. But it's a little bit deceptive to say they're weightless. The explanation for that's going to come a little bit more later. We're going to have to talk about circular motion, but we'll touch on that when we get to that point.